So as far as research areas, there really are quite a number in my lab. Besides the desalination projects, the one I'm most excited about now has to do with the semiconductor industry and how they define dimensions at the smallest level. So if you're looking currently at the iPad that you carry around or your laptop, the dimensions that people are talking about is 22 nanometers, and this is incredibly small when you think about human hair is 100 microns and a nanometer is 1,000 nanometers is a micron. So these are incredibly small dimensions. We've been working in collaboration with a group from University of Chicago, Professor Paul Neely, who does something called directed self-assembly. And there you're looking at almost molecular level segregation to make the patterns. And in combination with the ultra-thin films from my group, we've been able to demonstrate features down to 7 nanometer dimensions, and this really comes from our ability to control the process, the chemistry, and the purity of the material. And one of the things that's really exciting is that the processes I use are generally from the family of chemical vapor deposition. This is widely used in the semiconductor industry to make inorganic materials, but here what we're using is to make organic materials, which are often done by solvent processes like spin casting. And because we're doing the CVD, we can actually get to a much higher purity and have a much higher degree of control over these organic films. And that's some of the reason that we were able to get to these 7 nanometer dimensions. So in the semiconductor industry, the feature size is really what drives the whole industry. There's something called Moore's Law, which talks about the performance of devices, and that's driven by dimensions. So all the power that you have in your mobile devices now is really a result of shrinking the dimension of them. So as you go down and reduce a factor of 4 in dimension, it gives you a factor of 16 per area in the functionality of the device. So you can have a computer that runs that much faster, uses that much less energy. One question is why are we interested in organic surfaces rather than inorganic surfaces? So organic surfaces in and of themselves have properties which are different than the inorganic ones. They tend to be flexible. They tend to have a wider range of surface energy. So for example, the fluorocarbon films are really low surface energy, and they lend themselves to release surfaces, whether that be for rubber molding or ice-phobic surfaces or clathrate phobic surfaces, as well as really high surface energy, things that are really wettable. And they also have specific bonds that allow you to do things like attach nanoparticles covalently, attach proteins covalently, and those kinds of things allow you to make all kinds of sensors. So the organic the whole world of organic chemistry is quite rich, and this technique opens up the ability to put all of that on surfaces rather than just being solvated in a solution. So as far as cultures which haven't always valued this transition to practicality, I think there's a feeling sometimes that the end use somehow limits your intellectual endeavor, that you'll miss the big picture because you're so focused on trying to get this one idea out into the world. But I've actually found that the inverse is true. By actually trying to take your idea out, you ask a different set of questions and you come back richer for the experience. I can speak with my own personal experience about the first company, GVD, that I spun out, and I spent a sabbatical there, and I came back from the sabbatical saying that markets are harder than molecules. I'd become very good in the lab about getting molecules to behave in the ways that I wanted them to get the kinetics and depositions rates right, and the defects and all of these things. But you know, markets are much more complicated. Your knowledge of those is less important, and so actually talking to companies and understanding what the real problems are makes you go back to the lab and say, well, you know, I need to do this, plus I need to use a precursor which is environmentally benign or has a certain cost point. And these are really important. So this is where MIT, which has had the Industrial Liaison Program for a long time, really brings companies and allows you to have those interactions, and that's extremely important.